Check, 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 check. 1 2 1 2. Okay.
zero inclination orbit. This is close to the most intense regions of the inner belt. So we can use computer models of what's in the belt. The most popular one, I think, are called AP8 and AE8. That's P for protons and E for electrons. This model was developed in the 1970s based upon satellite data. There are better models that exist, including AP9, predictably. On top of that, we need to account for the spacecraft's orbit, so we need to calculate orbits, and we need to be able to convert the particles that we observe and their energies into a radiation dose. And that isn't trivial because you can't just take the number of particles and multiply them by a magic number. You have to account for the energies, which are spread out, and the different types of particles involved. And you also have to account for the effects of shielding, right? If you're in the spacecraft, you have a hull. And that isn't trivial because the effectiveness of a shield depends upon the type of particle and it depends upon the energy of the particle. And furthermore, the shielding itself can generate secondary radiation that also needs to be modeled. So the good news is all these different systems are actually modeled and handled for you on websites that are designed for people that design space missions. And the one that I'm using is the European Space Agency's Space Environment Information System, also known as SPENVIS. So if I place a hypothetical astronaut in a 3,000 kilometer equatorial orbit with no radiation shielding, and then I model everything out, it tells me that that poor astronaut would be exposed to a whopping 26,000 rads per hour. And yes, that would be fatal inside an hour, but that is unshielded, no spacesuit, so they're going to die even faster just due to asphyxiation. So if you add a few meters of aluminium to represent the skin of a spacecraft, then the dose drops significantly. Lots of the exposure actually comes from low energy protons that are really easy to stop. For the Apollo program, the natural shielding of the walls of the spacecraft were calculated to be roughly equivalent to about 7 millimeters of aluminium. And I know this because for Lunar Orbiter 1, they carried a radiation sensor to the lunar orbit, and it had two windows on it. One was 7 millimeters thick to represent what the astronauts would feel inside a spacecraft, and the other was 1 millimeter to measure the effects for astronauts on EVA. So if you add 7 millimeters of shielding, the dose drops from 26,000 down to about 20 rads per hour. And that's obviously a huge improvement, but it will still kill you in a few days if you were stupid enough to carefully maneuver your 1960s Apollo spacecraft into the middle of the radiation belt and then sit there doing nothing. I guess you could sit there and watch Chernobyl. So, let's come back to those conspiracy-minded people who claim that this level of radiation would make it impossible to go to the moon. Let's humour them. Let's simulate the orbit of a spacecraft headed from low Earth orbit out to the moon. This takes a few hours to cross all of the belts and beyond the outermost belts. And in those few hours, again, an unprotected human would receive about 1 million rads. But again, this is totally unprotected. If you add shielding, it makes a huge difference. It brings the dose down from 1 million to 3.6, which is actually pretty great given that it takes about 50 rad to start having visible short-term effects. It's even below the annual limits imposed on nuclear workers. But to be fair, we do have to double that because the crew will also need to come home via the same route. And these numbers, while mathematically correct according to the models, they're not accurate because I've been acting like Khan from Star Trek 2, thinking two-dimensionally. The orbit I used was in the equatorial plane, just like in Kerbal Space Program. It was close to the heart of the belts, but the radiation gets weaker as you move away from the equator. And most lunar transfer orbits will actually pass above or below the most dangerous regions. Just taking that simple orbit and adding an inclination of about 35 degrees, which many of the Apollo spacecraft did, that drops the dose by a factor of 20 down to 0.18 rads. And I'm just doing the barest minimal math to find an orbit which evades the core of the belt. When NASA was sending the Apollo spacecraft to the moon, they had this in mind and they made plans to make sure their spacecraft would avoid this. So look, for all the intense radiation in the belts, There's actually no problem crossing them. You just have to spend as little time as possible in those belts and choose trajectories that avoid any of the dangerous parts. The real truth, though, is that the radiation danger when going to the moon and further afield is from sources other than the Van Allen belts. Once you move outside the magnetic field of the Earth, you're exposed to high energy photons from the Sun. And most of the time, this proton flux is low enough to not be concerning. But the Sun is active and it can have flare ups and solar storms, which can emit enough radiation in a short period of time to be really dangerous. For example, in August of 1972, a powerful solar storm occurred, and NASA was really fortunate that this occurred between Apollo 16 and Apollo 17 rather than during any of those missions. If there had been a mission in progress during this flare up, the crew in their spacecraft would likely have had some symptoms of radiation sickness. But even worse, if it happened during an EVA on the surface of the moon, the suits wouldn't offer very much protection, and it's highly likely that that dose from that event could be fatal to an astronaut. Now, nearly 50 years on, we understand the dynamics of the sun a whole lot better. We have superior instruments for monitoring the solar weather and the solar atmosphere, but still predicting an energetic event like this